Hello, I'm Ed Gatzke, and this is first video in the Summer Program for Research Initiative, SPRI program, targeting mostly students at the South Carolina Governor's School. We usually do this in person on campus at the University of South Carolina, and I usually coordinate the program with the different research projects, but this year, because of quarantine and social distancing, we're doing virtual research, so that means students will be working on computational or non-experimental projects with their research PI. So start off this video with an introduction. Who am I? I grew up in Huntsville, Alabama. Both my parents were rocket scientists. Mom worked on Apollo and Dad worked on missile defense. I went to Georgia Tech for my undergraduate four-year degree. Then I went to graduate school, started at Purdue, and then went to Delaware. Finished my PhD there and then did a postdoc at MIT. I've got two kids in Blythewood High School. They're active in scouting. I'm scoutmaster for my daughter's troop and assistant scoutmaster for my son. He's going to be a sophomore. She's going to be a freshman. We live out in the northeast of Columbia. My research work is in chemical process automation and numerical methods. So that basically means robots for chemical plants, trying to keep plants safe and from blowing up. I also work in success and retention for our students. I'm the advisor for our Toastmasters Club, which helps students develop their speaking skills. And my wife and I have been taking students to a Maymaster 2-week trip to Germany on energy. And I'm faculty advisor for the engineering computing community, which is a group where students live in one residence hall together, so we can work with them on being successful in the college. Classes I usually teach, process control and dynamics. Basically, again, robotics for chemical plants. It's like the thermostat in your house, keeps you hot or cold depending on what you set your temperature at. But there's a lot of math that goes into analysis to make sure you have a nice stable system so that you can actually track your set points. And it's a lot harder when you have multiple variables that you're measuring and trying to control. Modeling numerical methods, I've done this for chemical and biomedical engineers. Basically, it's computer programming applied to solving engineering problems with math. So how do you write code to solve simulation problems and find things that, solutions. And we're going to expose you to some of that stuff, these topics in modeling numerical methods before you get started to research or at the early part of your research. I've also worked at Project Lead the Way. We would bring teachers onto campus and teach them how to teach pre-engineering classes in the high school and middle schools. And I looked at aerospace and mechanical engineering, so I've seen a lot of different topics. Traditionally, I've done some Carolina Master Scholar Duke Tips classes for middle school and high school students in robotics, energy, general engineering, aerospace, and like I said, ethics and professional development. I usually teach a class on its basic stuff, but sometimes people still need to hear how to interview, how to develop a resume, how to get the interview, how to deal with just going to career fairs, all those kinds of things, and lots of other things along the lines of ethics and professional ethics get into being successful in your career. One thing, I don't know if it's famous, I've got a YouTube video, if you may not show up on this video today, but it's stuck in a cornstarch pool. If you look for that on YouTube, you might be able to find this video that I took a few years ago at our E-Week. We get 1,000 pounds of cornstarch and we make a video, or we make basically a cement mixer so that it turns into a non-Newtonian, it acts like a solid in some cases when you put force on it, and it turns into a liquid in other cases. Years ago, I was at the Alabama Governor's School. We only did a 2-week summer program. We didn't have a stay away summer program. And I remember one of the famous researchers came to talk to us. He was on the Human Genome Project, which was something that's a big deal back in the early 90s, very new stuff. He said, "You're not going to remember this stuff, but you're going to remember this about the travels I've been on for my research work." And I remember that statement, and I was thinking something I've done a lot of is traveling. I lived in Germany for a year, so when we lived there with a family, we got to go around to a lot of different countries. It's just a simple drive. It's like driving to Atlanta or driving up to Raleigh, not too far away in most cases, to get to a lot of different places. We had to fly to Greece, but all the other ones, I guess we flew to the UK and Ireland too, but in general, it's so easy and things are pretty close together. It's just gas is really expensive. We even stopped by the small ones, Luxembourg, Liechtenstein. They have a little McDonald's and a castle. There's not much there. Monaco. We did the Monaco Grand Prix the same year that they filmed Iron Man 2 with the guy with the whips that was at Monaco. We sat right there for one of the practice rounds there. Andorra, which is a small little micronation between Spain and France. Vatican City, which is right in the middle of Rome. They have their own coins, their own euros that are specific to Vatican City. Some other travel I've done: Australia, Hong Kong, China, Japan, Thailand, Canada. So those are a lot of different spots I've been around, been able to go and visit for research conferences and different topics and interacting with people. Our family, we've been up and down the East Coast. We went to Vegas, Hawaii. On the wilderness side, Appalachian Trail, my brother and I have hiked on a good section of that. My son and I went to Philmont Scout Ranch for a couple of weeks last year, and both my kids are going to Sea Base in the Keys. So lots of cool stuff out there. If you get a chance, I think travel helps broaden your horizons, and you get to see more of the world. So that's enough on me. What we're going to talk about today, basically the overline for the virtual SPRI, we're going to talk a little bit about general research, give you a little Excel overview, do a little lecture on statistics and visualization methods. These are one video today, is just the research overview. A little bit on technical writing and PowerPoint and oral presentations. And I'll give you a couple assignments from my numerical methods class, which basically expose you to a little more advanced Excel, which is always a useful tool. But today we're just doing academic research overview. Like, what do we do as far as academic research? What is research? Basically, faculty members at a research university get funds to conduct research. And it basically comes out of corporate or academic laboratories. Most research gets done at a company that's doing research or a university that's doing research. There are some also national labs that do research as well. So those three are the main ones. Our funding at the university comes from government or companies or foundations. But the National Science Foundation, Department of Energy may write us a grant. Companies may come and contract us or talk with us or give us funds to support research. Or some foundations, like Cancer Society, may donate research to researchers. So your research, when you discover something, it can be presented at a conference or published. It depends on the domain, so it's not always true. But in general, most people will do some research and maybe do preliminary results at a research conference. There's lots of different conferences out there for every different specialization. Then you submit a paper into a peer-reviewed archival journal. So it gets put into these archival libraries. So in case there's a nuclear holocaust, there'll be these archival journal libraries lying around with all our sum total of knowledge tucked away. It also gets published in reports, which are not necessarily peer-reviewed. They're just published, books, and theses. So a PhD student may put stuff in a thesis that wasn't ever published, but in a journal or conference presentation. And it may also lead to patents and trade secrets. So if you're doing corporate research, you may not publish your work, just keep a trade secret and keep it quiet. Or you may patent it so that you can have a monopoly on that technology for, I think, 17 years. Peer review, we talk about that a lot. So when you have a peer-reviewed journal, you send your publication to a journal. The editor sends that publication out to experts in the field, and they read it and review it critically. It doesn't mean that they will replicate the results, but they may request more experiments or modifications or reorganize or whatever. You should look at this, you should try this. If it passes peer review, it will be published in an archival journal. Like I said, it goes to hard copy repositories around the nation and the world. And if it's a very substantial discovery, something fundamentally different. I mean, when I was in high school, cold fusion was a hot thing, and they couldn't verify it. I still haven't verified it, but it was a hot, big, substantial research topic, and immediately people worked to replicate results. But in general, most reviewers, just for the journal article, don't replicate the results. They just look to see if it's reasonable and if it's well presented and well organized. So when you're looking for research papers, that's one of the first things you'll probably be doing in your research group. You may be given some research papers. You may have to go to different databases out there and get papers. So the popular press web pages are generally not a good source for peer review. Although Wikipedia, people always say don't use Wikipedia for citing, but it's a good place to go in for learning, because it's usually a lot of the science and math stuff is usually in pretty good shape. You just want to cite it because any idiot can go out and modify Wikipedia. So you need to use these peer-reviewed papers for citations. Look at the journal title, and you may want, if you can find an impact factor, that's what measure of the quality or the impact of the journal, how much it impacts other research topics. Google Scholar is one out there, but it has a lot of questionable sources, a lot of random PDFs that they find online. There's open access journals where you don't have to have access to pay. University resources. There's lots of USC has great access to electronic resources, but unless you're affiliated with a USC login, you may have trouble getting those. So you may be stuck doing stuff on your own with Google Scholar and open access journals, unless your PI you're working with gives you a stack of PDFs that they can find because they have access already. There's another thing that's interesting. It's called interlibrary loan. So if I'm at USC and I find a paper that I want in the database, but we don't have it in our actual stacks at the library, a lot of times, like a conference, there may be a conference where they have proceedings, and that proceedings is published from the conference. So it's peer-reviewed. It's not a peer-reviewed journal, but it's a peer-reviewed proceedings from a conference. And it might be an interesting paper I want, but it's not very widely distributed. But it may end up in somebody's library, and I could find it through a database. If I can get enough information, the interlibrary loan system will get me a copy of that publication. Could be a book, they send me the book, or a scan of the book. So this is something a lot of libraries will go back and forth with. So it's amazing. A lot of the older journals these days have gone online, so a lot of them are on electronic. But if you find something obscure that you can find a location for it, they might be able to find it through interlibrary loan. It may take a few days or even a few weeks, but it's just amazing that all the libraries coordinate that way. So next up is, these are some slides I borrowed from Dr. Mike Matthews. He's our Senior Associate Dean for Graduate Research and Graduate Education. And this is slides I've taken from a class that he teaches for biomedical engineers. It's actually for graduate students in biomedical engineering, but anybody doing research should be exposed to a lot of these topics. So it's not super high technical level, but it's basics of what we're talking about today, research and how you're supposed to be doing research. So again, you want to discover new knowledge. That's what we're doing, advancing the knowledge base, because it helps state, nation, and world. Another objective is to help prepare next generation researchers and leaders. So that's why we have this program for you high school students, so that you can work on learning how to do research. You go to undergraduate and you're working on an undergraduate degree, but a lot of our talented undergraduate students will conduct research while they're an undergraduate. You're not working 40, 80 hours a week as a researcher. You're working in your spare time, but you can still do undergraduate research and be productive while you're working on your undergraduate degree. I did that as an undergraduate at Georgia Tech, and that's why I ended up going to graduate school, because I'm like, I like doing this. I worked at a paper mill in the summers, and I decided I'd rather go to graduate school and work on a research thing where I'm working on learning and developing new things instead of a traditional chemical engineering job. So discovery and education, these are the reasons we're doing all this graduate research and undergraduate research. Now, this is a cartoon on what is a PhD, and I have a link up there. So if you have a circle that's all human knowledge, when you finish elementary school, you know a little bit, and then high school, you know a little bit more. You keep learning knowledge. You don't know everything by any means. Bachelor's degree, you get maybe focus on one area. So for me, it was chemical engineering. That's the thing I went into. Master's degree and a PhD, start reading these papers, take you to the edge of knowledge. You get up to the focused area. You know what you're doing. You focus in one area. You've learned a lot about that topic. It could be deterministic methods for nonlinear optimization. It's whatever your topic is, you learn that to the edge of human knowledge. You focus down, you work on an area, and you poke at that boundary, trying things, learning things, looking for a discovery that helps expand science. Eventually, that boundary gives way, and you've done a PhD. You write a few papers, you've expanded the body of knowledge just a little bit. Of course, everything looks a little different because you've been so focused on one topic. It looks a little different to you, but you got to remember the bigger picture. There's a lot of stuff out there. So I thought that was an interesting little cartoon. So keep pushing. We're trying to expand that body of knowledge in all directions. It's not just one thing, but there's lots of stuff out there. And I think having a broad base of knowledge helps you in many cases, because one area, in at least my area of research, you can learn different areas, and if you can put them together, you can find something new that's new and novel, and maybe a contribution because you're drawing from multiple areas. This cross-disciplinary work. So, well-dressed PhD, solid academic core, something valuable research, independent, motivated, scholarly results well written, well presented. You're literate. Deal with the information. These are the kinds of things we're looking for graduate students. Not necessarily when you start, but in general, these are the things that you should develop if you get into graduate school. So you're being able to develop all those different aspects of your personality. Your starting points, you may have a broad knowledge of discipline, broad experimental approaches, some ideas, how to choose important problems and how to have some insights from those problems. But then this is the other stuff that's, you have to have, all of this stuff is related. Ability to read, and ability to plan, experiments, how to think clearly, and depth of knowledge. So all of that goes together. These are the concepts that work together. Having new ideas, being able to have mechanics, and having a good foundation. So you have to work on a foundation for your high school undergraduate, but then you also have to be creative and know how to do the other things. So there's a Pasteur's quadrant. You can do pure academic research just for fundamental understanding. My wife is a PhD chemist. She worked with rhenium, and that was her PhD. And I asked her, why are you doing that? And she said, well, nobody's ever looked at these molecules. Nobody's ever made these compounds and characterized them and understood them. I'm like, well, why are you doing it? Are you curing cancer or making a product? I'm like, no, we're just trying to understand them. It could cure cancer, but they weren't testing it for that. So pure, like Edison, would be not caring about fundamentals, just making it work. And that's more on the engineering side in a lot of cases. If you have a mix where you're trying to do both, make things better, but also understand why at the fundamental level, that's usually use inspired. So one of the things you're eventually going to do, you'll do some presentation of your work, but in general, you got to keep in mind, what are you trying to accomplish? Can you articulate this without using specialized words? How is it done today, and what are the limits? So you have to understand, why are we looking at this? Why is this an important problem? Why do you think whatever you're doing is new, and why do you think it's going to be successful? Who cares? If it's successful, will it make a difference in people's lives? Are there risks? Are there costs? How long will it take? These are kinds of questions you should probably be asking the first week. Start thinking about the first week or two in your research project. So why are we doing this? Who cares? All these kinds of bigger picture problems before you dig in too deep. So this is a good thing to, when you're writing up a paper, to pull together all of this stuff. Broad purpose, what are your specific questions? How did you get the information? What are your new information? Depth of research. Put all these kind of things together into a paper. So your purpose and specific questions. You generally move from your purpose to objectives in the beginning, your introduction, and then you move from broader purpose, narrowing down to specifics, your inverted pyramid, trying to get more and more focused on exactly what you're doing. Near the beginning, you have a literature. You look at all the literature that's relevant. You put in experimental methods to justify and explain what you're doing. So you put literature, and then you have some of the background information, the tutorial nature. So a lot of papers, if you're reading them, they'll have this in this introduction area. That'll oftentimes be the most useful stuff out there because it's in the paper, because it has some tutorial work. It helps you figure out what else is going on. Your results, discussion, conclusions. You have to interpret what you've done and why it's important. So you bring in some breadth and depth. You basically explain what you did and why it's interesting. So your literature review is something you'll probably start with in your in a paper, and you may be doing a lot of literature reading this summer. Honestly, if I were a PI, just reading a lot of literature and learning about a topic for 3 months or whatever, I guess we're doing 10 weeks. If you can do that and read a lot of papers and ask questions and learn, that's a great opportunity for you to spend time working with a PI and asking questions, just literature review over and over and over. Hopefully you'll be doing some work and actually working on research where you're developing something and helping with a project, but you may be doing a lot of work. So critical literature review, what's the purpose? You need to look in, if that's, a lot of times you have a lit review paper which has just maybe 100 or 150, 200 papers in it, and it will look in, but every journal paper will have a little bit of literature review in it, so it has some analysis of the relevant papers that sort of relate, some that are very relevant, very similar, contrasting different ideas, may have tables and graphs for comparing the literature review to help motivate what's going on, and it gives you some insight into what you're doing. You want to synthesize knowledge and bring these concepts together. So your lit review can take a long time to develop because it's basically the start of your paper. It's setting the stage for what you're going to do. This is all the stuff that's out there. Like we said, now we're going to try and do something new and why we think it's going to work. And these are the results. And this is why we think it's an improvement over the existing. So it's really setting the stage for why your paper's worthy and why your proposal needs funding or your thesis merits you getting your degree. So this lit review is a substantial part of your work. Think about your audience. So any gaps in knowledge. Some people may not know about all the papers. It's a little bit tutorial in nature as well, and it needs to be, a lot of times literature out there is not consistent, and experimental work may not have the same units or formatting, so you have to maybe do a little bit of juggling to get things in a nice format. Now here's another topic with 8 elements of thought: purpose, question, assumptions, point of view, data, concepts, inferences, implications, and consequences. So this is something, this is sort of a more talking about in general what we're doing and why we're doing it, and sort of thinking about thinking. So elements of thoughts, I'm not going to go into much detail here, just want to put it up there. So you got your purpose, why are we doing this? Questions, what are my specific questions? What am I looking to? And these correlate to introduction and conclusions. Why is your work relevant in your paper or your presentation? So your concepts and information, what are you really focused on? What's the background and of what we're building on? What are our methods that we're using? What's our results? This is the information is the core part of a paper because it's what you've done in your discussion and why it's important. Your conclusions, I guess, are really why it's important. That's where this is why it's important, why it's an improvement, recommendations or suggestions for future work, and implications that can be bigger reaching. Why, if this were actually productized, we could make zillions of dollars potentially. And point of view, so acknowledgments, who funded it, that kind of stuff, the conclusions at the very end. I want to pull up a paper. This is related to 2010 Nobel Prize in Physics for finding graphene, which is a carbon molecule. So a lot of times if you're given a research paper, the title will have some information, but the first thing you probably want to look at is trying to get through the abstract and seeing if you can understand. The abstract should have an overview of the contribution without too much jargon in it. So that abstract may have some, well, why is this important? It's only a few sentences, it's not too hard to read it, and it shouldn't have a lot of equations and stuff in the abstract. In fact, it generally won't have any equations in the abstract. Early on, there's a lot of literature review and tutorial information. So you can look for other papers that may be useful to read in the lit review. If you find a good article, dig up the lit review from that article and dig into what the foundation for the paper you're interested in. If you're looking in one paper, you want to look underneath it. What did they cite? So look through those other papers and look for tutorial information. If you don't have to read through and understand the entire paper at first, you may want to just thumb through and look at the figures and equations and see if you can wrap your head around what are they doing and why are they doing it. Sometimes visual is a lot easier than trying to go through all the words and equations on the paper. You may have to go back, if it's a really important paper in your area, you may have to dig through it and understand every single word in the entire paper. But at first glance, check that title, check the abstract, check the intro and tutorial nature and the figures. We're going to talk more about visual and how you use figures, but you have to be able to understand the figures in the paper and to communicate your data. How do you present it? There's a lot of different ways to present, and your PI will have probably standards for your research group, but I'll give you some information as well. So why are the conclusions? Why is it important? What are the references? So the other references are out there. What else are people doing, and what have they had success in? So those are the basic key points in a research paper. Before we go today, I wanted to talk a little bit about ethical and professional standards, which gets into plagiarism. So ethics are the rules of conduct, your rules that you deal with usually we talk about professional ethics. So chemical engineering has a rule of ethics. Electrical engineering, you look up ethics. It's not the same as your personal individual moral principles that you live on. So it's your rules for proper professional behavior. There's research misconduct you can deal with, plagiarism, publishing and authorship often is a big issue, proper citations. Those are the main ones that a lot of students get in trouble with. Later on, you can worry about intellectual property and export controls, subjects if you get into biological areas, biosafety, but the main ones we want to talk about are these ones in red that students often have trouble with. So falsification of data, fabrication of data, like your PI wants you to come up with something, you can't do the calculation, you can't get to work, your experiments don't work, all of your cells die, whatever happens. Sometimes there are cases where the students or researchers will falsify or fabricate data. But the bigger one we're going to talk about is plagiarism. If you plagiarize, you might have to retract a paper, take away degrees, loss of funding, loss of your job, depending on where you are, job restrictions, career track, so institutional fines, lots of bad stuff for plagiarism. So taking someone's ideas, methods, or words without acknowledgement is basically what plagiarism is. So you can take ideas, but you can also plagiarize text. We usually think about copy pasting off the internet. I had a student once, I'm like, this is a strange way to write this paper. They're supposed to write just a couple pages on something they wanted to invent, and they had written in their paper, using our patented technology, we will be able to bring this product to market. So they just cut and paste off the internet without even reading through what they were cutting and pasting. It's terrible. So you can also plagiarize ideas and inventions. So if you have knowledge of somebody, you can, if they take their invention or creativity and don't cite them, that's another potential plagiarism. So you need to know the literature, cite sources rigorously, paraphrase properly without using the exact same words. So the rule I was always told, read the paragraph, read the page, and then put the book down or put it away, and then rephrase it in your own words, and then cite it as well. So summarizing and paraphrasing. If you want to quote exactly, you have to learn how to quote exactly and cite all that stuff for others. And that's basically a quick overview, introductory video for the program and some ideas about research and conducting research and reading papers and understanding why we do it and some of the stuff that you might run into as far as plagiarism. So I'll have a few more videos for you guys in the upcoming days.